And today we're tackling a research paper that one of you actually sent our way.
That's right. A listener suggested this one, so a big shout out and thank you for sending this in.
Yeah, absolutely. And it's a pretty dense one, as you might imagine from the title. So we're gonna do our best to kind of distill it down. But the full title, if you want to look it up yourself, is Fluid Structure Interaction Analysis of Pulsatile Flow in Arterial Aneurysms with Physics-Informed Neural Networks and Computational Fluid Dynamics.
Yeah, that's a mouthful for sure.
It is from Physics of Fluids, and the request was really to understand, what this tells us about vascular health, and particularly with respect to Marfan syndrome. So that's going to be kind of our North Star as we go through this deep dive.
Yeah, absolutely.
All right. So to set the stage, you know, we kind of have to acknowledge just how big of a deal cardiovascular disease is.
Oh, absolutely. And the paper kind of hits us with a pretty alarming statistic right up front.
Okay. Yeah. What's that?
It says that over 92 million adults in the U.S. are affected by some form of cardiovascular disease. And get this, they're projecting that by 2030, almost 44% of the population could be affected.
Wow. That's a huge chunk of people.
It is, and it really highlights why research like this, that's trying to understand these conditions in detail, is so vital.
Absolutely. And this study hones in on aortic aneurysms. So before we go too much further, maybe just define that for anyone who might not be totally familiar with that term.
Sure, so an aortic aneurysm is basically a bulge in the wall of the aorta.
Okay, and the aorta being...
The aorta is that main artery that carries oxygen-rich blood away from your heart to the rest of your body.
Got it, the big one.
The big one, yeah, exactly. And an aneurysm happens when a section of the aorta wall weakens, which allows it to balloon outwards, kind of like a weak spot in a tire.
Okay, and so what makes an aneurysm form in the first place? Like, what causes that weakening?
Well, there are several risk factors. Age is a big one. The older you get, the more wear and tear on your arteries, so to speak. High blood pressure is another culprit because it puts constant stress on the vessel walls. Smoking damages the arteries and can also contribute. And then there's the buildup of plaque from things like high cholesterol that can narrow and weaken the arteries.
Yeah, the usual suspects there.
Right. But the paper also highlights the role of genetics, and that's where Marfan syndrome enters the picture.
Okay, so that's kind of the link we need to explore here.
Yeah.
Like, how does Marfan syndrome tie into all of this?
So Marfan syndrome is a genetic disorder that affects the connective tissue throughout your body.
Connective tissue now, that's...
It's basically the stuff that holds everything together. It provides structure and support for your organs, your bones, your skin, even your blood vessels.
Okay, the scaffolding.
Yeah, exactly, the scaffolding. And in Marfan syndrome, there's a problem with a specific gene that's responsible for making a protein called fibrillin-1.
Fibrillin-1.
Okay. And this protein is crucial for strong and healthy connective tissue. So when it's faulty, the connective tissue is weaker and more prone to stretching or tearing.
Oh, so that's got to be a problem for your aorta.
It is big time because the aorta being the largest artery, it's under a lot of pressure from the blood flow. So if its walls are weak, it's much more likely to develop an aneurysm.
And it sounds like it's not just any aneurysm, it's specifically where it happens that could be particularly dangerous with Marfan syndrome. Is that right?
That's right. In people with Marfan syndrome, these aneurysms often form in the ascending aorta.
Ascending. Yeah.
The section of the aorta that comes right out of the heart and curves upwards is sort of the first part of the aorta. And if an aneurysm there ruptures, it can be life-threatening.
Okay, so we've got the weak spot, and we've got kind of the worst case scenario location-wise. But the research goes beyond just the structure of the aorta.
Yeah.
It also really delves into how blood flows through it, which I found super interesting.
Yeah, it gets really fascinating here because it's not just about the shape of the vessel, but also the dynamics of the blood flow, how that blood is actually moving through the aorta that can impact how an aneurysm develops and whether it's likely to rupture.
So how do they even begin to study that?
Well, the paper focuses on two key forces, wall shear stress, or WSS, and von Mises stress.
Okay, so WSS, what's wall shear stress exactly?
Imagine you're standing in a river and you feel the current pushing against your legs.
Okay.
That's kind of like what wall shear stress is. It's the force of the blood rubbing against the inner lining of the artery wall. And this force can actually influence the cells that make up that lining, the endothelial cells.
Oh, interesting. So it's not just a passive thing. It actually affects the artery itself.
Exactly. And the study emphasizes that when WSS is too low, which they found happening inside the aneurysms in their models, it can disrupt the normal function of those endothelial cells and increase the risk of things like blood clots forming.
Okay, so you don't want it to be too sluggish in there.
Not at all.
And what about von Mises stress? that sounds like it's looking at a different aspect.
Yes, von Mises stress is a measure of the stress within the material of the artery wall itself. So rather than the force of the blood, it's more like how much tension the wall is experiencing from being stretched or pushed.
Okay, so like how much it's straining to hold everything together.
Exactly. And the higher the von Mises stress, the greater the risk that the aneurysm will rupture.
So those are the two big players they're looking at. And how do they actually measure or analyze these forces in the aorta?
They use a really cool method called computational fluid dynamics, or CFD.
CFD? Now that sounds...
It's basically like creating a virtual version of the aorta on a computer and then simulating how blood flows through it.
Okay, so they're building like a digital model of the aorta and the blood.
Yeah, and they can tweak all sorts of parameters like the shape of the aorta, the properties of the blood, and the pulsing of the heart to see how those things affect the forces on the wall.
Wow, that's pretty high tech. And how many aortas did they model in this study?
They used 6 different models in total.
6.
4 of those were aortas with aneurysms from patients with Marfan syndrome.
Okay.
And then they had 2 healthy aortas as a control group so they could compare and contrast the results.
It's a good mix there to see what the differences were.
Right. And they got these models from a database of vascular models, so they were based on real human anatomy.
Okay, so before we jump into the results, what kind of assumptions did they make when they were building these simulations? I mean, obviously blood flow's incredibly complex.
Right. They had to make a few simplifications to make the simulations manageable, but they tried to keep things as realistic as possible.
Makes sense.
Yeah.
What were some of the key assumptions?
Well, first they assumed that blood behaves like a Newtonian fluid, which is a reasonable approximation for large arteries where the flow is relatively fast.
Newtonian fluid. Now, I vaguely remember that from physics class, but remind me what that essentially means.
It basically means that the blood's viscosity or thickness stays constant regardless of how fast it's flowing.
Okay, so it's not like honey, which gets runnier when you stir it.
Exactly. Unlike honey, blood behaves more like water in this context, at least in the large arteries.
Got it. Makes sense. And what else?
Well, they also used a specific model called the shear stress transport, or SSTKX turbulent transitional model, to account for the fact that blood flow can get a bit chaotic.
Turbulent.
Yeah, exactly. So this model helped them simulate the swirls and eddies that can occur, particularly around bends and branches.
Okay, so they're really trying to capture all those nuances of blood flow. And what about the interaction between the blood and the artery wall itself?
Ah, this is a crucial point. They took into account what's called fluid structure interaction, or FSI.
FSI. Okay, tell me more about that.
So imagine a garden hose with water flowing through it. If you squeeze the hose, the water pressure changes and the shape of the hose changes too, right? Well,
Yeah.
FSI is kind of like that. But for the blood and the artery wall, they're constantly influencing each other. The blood flow puts pressure on the wall, which can make it stretch or deform. And those changes in shape can, in turn, alter the blood flow pattern.
It's like a dynamic dance between the two.
Exactly. And lastly, to mimic the beating of the heart, they used what's called pulsatile inlet velocity. So the blood flow wasn't just a steady stream, it pulsed in and out with each heartbeat.
Okay, like a wave.
Exactly. So they really tried to capture that realistic pumping action of the heart.
Super cool. So with all of that in place, what did they find when they ran these simulations? How did the results for the healthy aortas compare to those with aneurysms?
All right, so in the healthy aortas, they observed a pretty uniform distribution of wall shear stress, or WSS, meaning it was relatively consistent throughout the vessel.
Okay, so no big spikes or dips in the force on the walls.
Right, and the values they saw were generally below 40 pascals, which is considered a healthy range.
Pascals being the unit of measurement for WSS.
Exactly, it's a measure of pressure or force per unit area.
Okay, got it. And were there any exceptions to that uniform pattern in the healthy aortas?
There was one interesting observation. They did notice higher WSS in the carotid and subclavian arteries, which are branches that come off the aorta.
Okay, why would those areas have higher WSS?
Well, they think it's probably due to the smaller size and the sharper angles of these branches compared to the main aorta.
Makes sense. If the blood has to squeeze through a narrower passage, it's going to exert more force on the walls.
Exactly, and that's kind of what they saw happening in the simulations.
Cool. So pretty consistent WSS overall in the healthy aortas, except for those branch points. What about the aneurysms? Was it a similar story there?
Not at all. The WSS distribution in the diseased aortas was much more irregular.
Irregular meaning?
It varied a lot from one spot to another, with some areas experiencing very low WSS and others having much higher WSS.
Okay, and what about the magnitude of those forces? Were they similar to the healthy aortas, or was there a difference there too?
There was a big difference. They found that the WSS within the aneurysmal sac itself was significantly lower than in the healthy aorta.
Lower WSS now, is that a good thing or bad thing?
Well, remember we talked about how low WSS can disrupt the function of those endothelial cells that line the artery,
Right.
and it can increase the risk of blood clots?
Okay, so sluggish flow in the aneurysm is actually a problem.
It can be, yeah, because it can create a sort of stagnant zone where blood clots are more likely to form.
Interesting. And they saw this pattern consistently across all 4 of the Marfan aneurysm models.
Yes, they did, which suggests that it's a common feature of these types of aneurysms.
Okay. And what about the higher WSS that they observed in some areas of the diseased aortas? Where was that happening?
It was a similar story to the healthy aortas. They saw elevated WSS in the carotid and subclavian arteries.
Okay, so even with the aneurysm, those branch points are still kind of trouble spots in terms of high WSS.
It seems that way, yeah. And they think it's likely due to a combination of the geometry of those branches and the altered hemodynamics. The overall blood flow patterns are different in the diseased aorta.
Got it. So it's not just the shape of the branch itself, but also the way the blood is moving through the entire aorta that's contributing to that higher WSS.
Right.
Okay. And the study also mentioned something about the shape of the aorta itself, something called tortuosity. How does that play into all of this?
So tortuosity refers to how much the aorta twists and turns, how much it deviates from a straight line.
Okay, so some aortas are curvier than others.
Exactly, and this can have a big impact on WSS distribution, particularly in the diseased aortas.
How so?
Well, the researchers found that when the aorta is more tortuous, those curves and bends create centrifugal forces that act on the blood as it flows through.
Centrifugal force. So like when you swing a bucket of water around and the water gets pushed to the outside.
Exactly. The same principle applies here. The blood gets pushed towards the outer curve of the aorta, which leads to higher WSS on those areas.
So on the outside of the bend?
Yeah, typically on the back sides and top of the aorta, and conversely, you get lower WSS on the inner curve, the front side.
Okay, so even more variation in WSS depending on the shape of the aorta.
Right. And this can further contribute to damage to the vessel lining and potentially worsen the aneurysm.
Makes sense. Now let's switch gears a bit and talk about the risk of these aneurysms actually rupturing. How did the researchers use their simulations to assess that?
This is where that von Mises stress analysis comes in. Remember, that's a measure of the stress within the wall of the aneurysm itself.
Right, so how much strain it's under.
Exactly. And by calculating the von Mises stress at different points in the aneurysm, they could identify the areas that were under the most stress and therefore at highest risk of tearing or rupturing.
Okay, so they're looking for the hot spots, the areas that are most likely to give way.
Right. And they did this for each of the 4 Marfan syndrome cases, MS1 through MS4.
And what did they find?
Well, each case was a bit different. For example, in MS1, the highest von Mises stress was on the superior side of the aneurysm,
To mirror meaning.
the top part.
Okay.
Whereas in MS2, the danger zones were more on the posterior and superior parts near the beginning of the aneurysm.
Posterior being.
The back.
Got it. And what about the other 2 cases?
In MS3, the highest stress was on the anterior side, but further down the aneurysm.
Anterior being.
The front.
Okay, and MS4.
MS4 was similar to MS1 with the highest stress on the superior side.
So some variation in where the weakest points were, but overall it seems like the superior side was a common theme.
It was, yeah. And what's really concerning is that when they compared all 4 cases, MS1 had the highest von Mises stress overall on that superior side.
So that particular aneurysm was under the most strain and therefore at greatest risk of rupture.
Exactly.
Okay, so they've got all this information about WSS Mises stress tortuosity, and then they throw in this whole other layer of complexity with these physics-informed neural networks, or PINNs. What are those all about?
This is where the study gets really cutting edge. PNNs are basically a type of artificial intelligence that combines the power of machine learning with the fundamental laws of physics.
Okay, that sounds super complicated.
It is, but think of it this way. Traditional neural networks, they're like sponges. They soak up data and learn patterns from that data.
Okay.
But PNNs are different. They're not just learning from data. They're also being guided by the equations that describe how things work in the real world. In this case, the equations that govern fluid flow.
So it's like they have a built-in understanding of the rules of the game.
Exactly, and that makes them really powerful because they can make more accurate predictions with less data, and they can do it much faster than traditional methods.
So faster and more efficient. That's got to be a huge advantage.
It is, and in this study, the researchers found that their PNNs were able to produce results that were very similar to the full-blown CFD simulations, but they did it with significantly less computational costs.
Wow, that's impressive. So it's like they're getting the same level of detail, but without all the heavy lifting.
Exactly, and that's why they're so excited about the potential of PNNs for clinical applications. Imagine being able to assess a patient's aneurysm risk in real time using a tool that's both fast and accurate.
Yeah, that would be a game changer. And how do they actually build the physics into these neural networks? I mean, how do you teach a computer about the laws of physics?
It's pretty complex, but essentially they incorporate the mathematical equations that describe fluid flow directly into the structure of the neural network.
So it's not just learning from examples, it's also being constrained by these equations.
Exactly. So if the network's predictions violate those equations, it gets penalized and it has to adjust its calculations.
It's like it's got a physics tutor built in.
Yeah, kind of. And they also feed in all the specific boundary conditions of the problem. Things like the fact that the blood can't slip at the artery wall and the pulsatile nature of the flow.
Okay, so they're really setting up the network to work within the rules of the real world.
Right. And they also used a special technique to automatically balance the importance of matching the simulation data with satisfying the physics equations.
So it's not just blindly following the equations, it's also taking into account the actual observations from the simulations.
Exactly. It's finding that sweet spot between the two.
Very cool. So big picture, what are the practical implications of all of this? How might this research actually help patients down the line?
Well, the clinical relevance is huge. This kind of research could lead to earlier and more accurate detection of aortic aneurysms, especially in people with Marfan syndrome.
Okay, so identifying them before they become a serious problem.
Exactly. And by understanding the hemodynamics, the way the blood flows through the aneurysm, they might be able to predict which ones are most likely to rupture.
So it's not just about the size of the aneurysm, but also how the blood is behaving inside it.
Right. And that could help doctors make better decisions about when and how to intervene.
So whether to monitor it closely, whether to do surgery, whether to prescribe medications.
Exactly. And potentially it could even lead to the development of new therapies that specifically target those abnormal flow patterns.
Oh, that would be amazing. Like something to normalize the WSS or reduce the von Mises stress.
Exactly. It's really exciting to think about the possibilities.
It is, but as with any research, there are always limitations, right?
Yeah.
What are some of the caveats we should keep in mind with this study?
Of course, no study is perfect, and the researchers themselves acknowledge a few key limitations.
Okay, like what?
Well, for one, their main focus in this study was on wall shear stress. They didn't really delve into other mechanical factors that could be important. Things like the elasticity of the artery wall, how much it can stretch, and how it responds to stress. They plan to incorporate those factors into their future research.
Okay, so more to come on that front, and what else?
Well, they also point out that while their models are based on real human anatomy, they are still simplifications.
Right, they can't capture every tiny detail of every individual patient.
Exactly, and there's always going to be some variation from person to person.
Makes sense. And anything else?
Well, lastly, it's important to remember that this study only looked at a small number of factors that can influence aneurysm behavior.
Right, there are all sorts of other things that could play a role.
Like genetics, overall health,
Hmm.
other medical conditions. It's a very complex picture.
Absolutely. So it's a great starting point, but definitely not the whole story.
Right.
Okay, so to wrap things up, what are the key takeaways here for our listeners? What do we really want them to remember from this deep dive?
Well, I think the big takeaway is that the way blood flows through our arteries is incredibly important, especially when it comes to things like aneurysms.
It's not just about the structure of the vessel itself, but also the dynamics of the blood flow.
Right, and this research highlights two key forces, wall shear stress and von Mises stress, that can play a big role in how aneurysms develop and whether they're likely to rupture.
And they saw clear differences in these forces between healthy aortas and those with aneurysms, particularly in people with Marfan syndrome.
Exactly, and what's really exciting is that they're using these cutting-edge computational tools like PNNs to analyze these forces in more detail and with greater efficiency than ever before.
So it's not just about understanding the problem, but also about developing better ways to diagnose and treat it.
Absolutely.
Okay, so for you, the listener, now you're armed with this knowledge. You can impress your friends at parties.
Or at the doctor's office.
Yeah, exactly. And it really underscores the importance of understanding these kind of complex biomechanical processes. It's not just about genes and risk factors. It's also about the physics of the human body.
Right, and how those physical forces can influence our health in profound ways.
And I think that leads us to a really interesting question that we didn't explicitly address in the paper, but it's something to ponder. We've seen how these computational tools could be used to analyze blood flow and aneurysms, but what other applications might there be in cardiovascular medicine or even beyond?
Yeah, it's a great question. Could we use similar techniques to study things like atherosclerosis or heart valve disease or even blood flow in the brain?
Or to design better medical devices or to personalize treatments based on an individual's unique anatomy and physiology?
The possibilities are really endless, and I think that's what makes this kind of research so exciting.
Absolutely. Well, on that note, we're going to wrap up this episode of The Deep Dive, but keep those amazing sources coming, and we'll be back next week to tackle another one.
See you then.
Bye, everyone.